Hi everyone, welcome to Lecture 13 on necessary and sufficient conditions. The objectives for this video are the following. After watching, everyone should be able to, number 1, define necessary conditions and sufficient conditions. Number 2, using the definitions, prove 6 basic properties of necessary conditions and sufficient conditions. And number 3, describe some concrete examples of necessary conditions and sufficient conditions. So the last couple of weeks we've looked in some detail at some of the big problems that's faced by inductive logic. For the remainder of the course we'll look not at the associated problems but instead at the developments that have been made that constitute progress towards the goal of constructing a system of scientific inductive logic. We're starting with the material in Chapter 5 called Mills Methods, which involve an analysis of causality and shed some light on the experimental method, which is one of the chief methods of scientific inquiry, to investigate statements of cause and effect. To analyze causality, we make two definitions of these things called necessary conditions and sufficient conditions. This makes things precise for us and avoids any linguistic ambiguities that might be associated with the word cause. We then talk about causes in terms of necessary conditions and sufficient conditions instead of using the word cause itself. The reason is that when the word cause is used in everyday English, sometimes it's used to mean sufficient condition, and sometimes it's used to mean necessary condition, and sometimes both, and sometimes neither. We'll then prove a few claims from the basic definitions. We'll prove these quite rigorously, so the structure of these proofs is something to focus on as we move through this video. So here are the important definitions. We say that a property F is a sufficient condition for a property G, just in case whenever F is present, G is present. And the second one, we say that a property H is a necessary condition for a property I, just in case whenever I is present, H is present. Now, let's look at some examples to help differentiate the two. Here's a square. Now, having four sides is a necessary condition for something's being a square. To argue why, we show that it satisfies the definition of necessary condition, so definition 2 up there. That is, we check that whenever something is a square, then it has four sides, and indeed this is true. However, having four sides is not a sufficient condition for something's being a square. To see why, we check that it violates the definition of sufficient condition, so definition 1 up there. That is, we check that it's not the case that whenever something has four sides, then that thing is a square. And to check that, it's enough to come up with a counterexample. So to come up with something that has four sides but is not a square. And there are lots of things that have four sides but are not a square. A rhombus is one. So it's not the case that whenever something has four sides, it is a square. So having four sides is not a sufficient condition for something's being a square. So let's pause and have a go at a question. Now, using the definitions of sufficient condition and necessary condition, we can very easily prove some basic properties of necessary and sufficient conditions. Here are two claims expressing two of those basic properties. Claim 1 says that if A is a sufficient condition for B, then B is a necessary condition for A. And claim 2 says that if C is a necessary condition for D, then D is a sufficient condition for C. Now, we're interested in justifying these claims, and to do so, we'll prove them using only the definitions themselves of necessary and sufficient conditions. Now, by a proof, I mean a series of statements, each of which follows logically from what has come before. It starts with things that we are assuming to be true, and it ends with the thing that we are trying to prove, so the statement of the claim. The focus here is on providing a particularly rigorous demonstration of these claims. This is a skill that we'll find useful as we move into the later chapters of the book, so we'll start practicing those skills properly here. Of course, if you've seen proofs before, either in this logic sequence or in a math type class, then this might be familiar. But if you haven't, not to worry. My advice, again, is that practice makes perfect. I'll model a few proofs here, so if you're less familiar with proof techniques, your task will be to go away and practice a few yourself using the questions in the assignments. So here's the proof of claim 1. Remember that proofs start with things that we're assuming to be true. So what are our assumptions here? First, we notice that claim 1 is an if-then statement. And to prove an if-then statement, what we do is assume the if part, also called the antecedent, and then show that the then part, which is also called the consequent, follows. So to prove claim 1, we suppose that the antecedent is true. We suppose that A is a sufficient condition for B. By the definition of sufficient condition, that just means that whenever A is present, B is present. Now we look at what we want to show, and what we want to show is that the consequent of the statement of claim 1 is true. We want to show that B is a necessary condition for A. By the definition of necessary condition, that means we want to show that whenever A is present, B is present. But we've already established that fact because we supposed that A is a sufficient condition for B, and that's just what it means for that to hold. So we've established what we set out to establish, and so that completes the proof of claim 1. And the little square down there indicates that the proof is complete. You would read the square as QED. Claim 2 is proved in a similar way. We want to start by stating our assumptions. Now, the claim in claim 2 is an if-then statement again, so to prove it we assume the if part, we assume the antecedent. So we suppose that C is a necessary condition for D. By the definition of necessary condition, that means that whenever D is present, C is present. Now we look at what we want to show. We want to show that the consequent is true. We want to show that D is a sufficient condition for C. By the definition of sufficient condition, that just means that we want to show that whenever D is present, C is present. But again, we've already established that fact because we supposed that C is a necessary condition for D, and that's just what it means for that to hold. So we're done with claim 2 as well. So here are 4 more claims that follow from the definitions. Claim 3 says that if A is a sufficient condition for B, then not B is a sufficient condition for not A. Claim 4 says that if C is a necessary condition for D, then not D is a necessary condition for not C. Now these are important to us because quite often we're interested in the absence of properties to check causal relationships, just as well as we're interested in the presence of properties. Claim 5 says that if A is a sufficient condition for B, then not A is a necessary condition for not B. And claim 6 says that if C is a necessary condition for D, then not C is a sufficient condition for not D. Claims 5 and 6 tell us how sufficient and necessary, those terms, interchange, depending on whether we're talking about properties or whether we're talking about their negations. Together with claims 1 and 2, the 6 claims we've seen in this video constitute some basic properties of necessary and sufficient conditions that we'll appeal to a lot as we move on through this week and next. Now, I'm only going to prove claim 3 in this video. The proofs of claims 4, 5 and 6 are in the assignments. The proof of one of those is similar to the proof I'm about to do, and then the proof of the other 2 are easier, so I'll leave those 2 in your capable hands. So here's the proof of claim 3. There'll be a little more input on your behalf this time as we walk through it. Now, just like the 2 claims we saw earlier, claim 3 is an if-then statement. So here's the first question. To prove claim 3, what do we do first? To prove claim 3, we start by assuming that the if part, or the antecedent, is true. So we suppose that A is a sufficient condition for B. Here's the next question. What does that mean? All that means is that whenever A is present, B is present, and that just follows from the definition. So here's the next question. What do we want to show? We want to show that the consequent in claim 3 is true. That is, we want to show that not B is a sufficient condition for not A. So here's another question. What does that mean? Well, by the definition of sufficient condition, that just means we want to show that whenever not B is present, not A is present also. Now, we know exactly what it means for a property not B to be present. We defined that all the way back when we looked at presence tables. And we know that a property not B is present just in case the property B is absent, and similarly for the property not A. So, to show that whenever not B is present, not A is also present, we have to show that whenever B is absent, A is absent. That's just what that means. Notice that this is just the same as showing that if B is absent, then A is absent. All I've done there is rephrase the whenever as an if-then statement. Now, we know what it means to prove an if-then statement. First, we assume the antecedent, and then we show that the consequent follows. So, to show what we're interested in now, we assume the antecedent is true, so we suppose B is absent. And then we want to show that the consequent is true. That is, we want to show that A is also absent. Now we're going to argue for the conclusion, so that A is absent, by contradiction. So we suppose the opposite of what we're aiming for is true, and we'll derive a contradiction. Now remember that this was the argumentative strategy we saw when we looked at Hume's problem of induction. That's how Hume laid out that problem. Now it will follow that the thing we were aiming for must have been true after all once we derive this contradiction. So we suppose for contradiction that the opposite of A is absent is true. That is, we suppose for a contradiction or towards a contradiction, like I've written there, that A is present. That's the opposite of A is absent. But now we remember our assumption from the very beginning, which is in blue on the slide there, which we haven't used yet. We assumed that whenever A is present, B is present. Now we've supposed A is present for a contradiction. So, by the assumption, B is present. But our subsequent assumption, this time the one in orange on the slide there, was that B is absent. And this is our contradiction. B cannot be both present and absent. So it follows that A cannot be present after all. So A is absent, and this is exactly what we wanted to show. So we're done with the proof of claim 3. Now, I appreciate that there's quite a lot of argumentative techniques going on in here. So again, the focus is on being patient, re-watching if you need to, and really focusing on the moves we're making when we prove something like we have here, understanding why we're making each step that we make. The only way to get good at proving things is to sit down and make yourself prove things, and the assignments will help with that. If proofs are a new thing to you, then the discussion sections will be a good time to practice them too and ask questions about them there. Now, the last thing I'll do is illustrate claim 3 with a concrete case. There'll be questions like this on the assignments too, so given a theoretical claim like the 6 we've seen in this video, it's good to think about concrete examples that illustrate those particular claims. Now, claim 3 said that if A is a sufficient condition for B, then not B is a sufficient condition for not A. To illustrate this using an example, I just mean saying something like the following. Suppose that a certain infection is a sufficient condition for a high fever, so that whenever someone gets this certain disease, they run a high fever. Then the absence of a high fever is sufficient to guarantee that a person is not suffering from this infection. So there's nothing complicated going on here, we just need to be able to translate what we've seen theoretically in the claims into concrete everyday examples. And that brings us to the end of this video. The real key takeaways are those 6 claims, or the properties of necessary and sufficient conditions, as well as the definitions themselves, of course. And the reason is that we'll use these claims a lot implicitly when we look at Mills methods, which is the topic of the next few videos. So do your self-reflection questions, and I'll pick up next time with the next topic.